This video contains an exercise which will help you calculate the number of free charges in a copper wire. You will also learn how to compute how many charges per second flow through the wire cross-section if the drift velocity, which is something we discussed in a previous video, is known to you. And the contents of this module here are somewhat more extensive, and also they remain relatively theoretical until the example at the end, so bear with me. It's worthwhile to follow the individual steps, as the definition of electric current and also electric resistance directly follows from the equations which we derive in this video. My name is Andreas from The Fearless Engineer, and here we go. Now, before we start with the exercise, let's briefly discuss what this is all about and why it makes sense to invest the time. By the end, somewhen we want to arrive at a sound definition of electric current, and this exercise here calculates the amount of charge that moves, that propagates through a conductor, in this case a copper wire, in a given unit of time. And by using the equation which we will derive in this video, we can very easily get to this sound definition of electric current. And this is our motivation. And the approach consists of 5 individual steps. First, we want to identify the knowns and unknowns and the quantities which we will be using throughout this exercise here. And in the second step, we want to compute the number of copper atoms in a given volume of 1 cubic centimeter. I will explain why it makes sense to use exactly this volume here, but this is what we get by the end of step number 2. And then step number 3 is to compute the amount of charge in the entire wire volume based on the results from step number 2. And in step number 4, we will determine the amount of charge per unit of time. We will assume a certain length of time, and then we will compute the amount of charge that propagates through a wire in this unit of time. And in step number 5, we will use the formulas which we have derived up until this point and use them to compute an actual numerical example from practice. Now, in the first step, let's talk about the known and unknown quantities for our problem here. The first thing we know is the cross-sectional area of the wire we are looking at. You can see this wire here on the right-hand side, cross-sectional area at the beginning and at the end of the wire. In between, there is the length L of the wire, which we also know. We also know the atomic weight of copper. If you have not yet encountered this expression, atomic weight, you might want to watch the video which I recorded on this topic some time ago. Also, we know about the density of the wire material, which is copper in this case. We know the value of the elementary charge, E-, and we also know the drift velocity of the electrons moving through the wire caused by an electric field E, which permeates the wire. And the unknown quantities, where we want to arrive at by the end, is the charge per time, Q divided by T. This is where we want to get to, and this is on the left side where we start from. Now, in the second step, we want to compute the number of copper atoms in a given volume, in this case 1 cubic centimeter. And since our target equation is charge divided by time, what we need to do first is we need to find the number of free charges in the wire that make up our Q. So we want to identify all the charges in the wire that are free to move about, the valence electrons, and once we have them, we have our Q, and then in the next step we can take a look at T. And in order to get the total amount of free charge, we have to look at the number of free electrons in the electron gas cloud. If you have not yet heard about electron gas, you might want to watch this video as well before you continue, because there I shortly explain what this model here, this concept, is all about. And in order to do this, in order to arrive at the total amount of free charge, we need to first calculate the number of copper atoms in a standardized volume, and in this case we use 1 cubic centimeter. And the blue circles here, they represent individual charges, individual electrons. Now let's start by finding out the atomic mass of copper and also the density of copper, which you can extract from the table of elements or from Wikipedia. And if you do so, you get these two values here. The atomic mass for copper is 63.546 grams per mole. Mole is a number, actually. It's the number of hydrogen atoms which make up 1 gram of hydrogen. It's also called Avogadro's number, and we have discussed it in a previous video. This first number here. And the second number is the density of copper, which is 8.96 grams per cubic centimeter. And this cubic centimeter here is the reason why we chose the volume of 1 cubic centimeter in the previous step. And by looking at the units of the atomic mass and also the density, we can notice that by dividing density by atomic mass, as shown here, we get the number of atoms in a known volume. So we cancel out the weight, grams, and what remains is mole divided by cubic centimeter. And since we know that 1 mole of a certain material contains 6.022 times 10 to the power of 23 atoms, this is Avogadro's number, we can now easily compute the number of copper atoms in this volume of 1 cubic centimeter. And we can do this by using this ratio here between density and atomic weight, multiply it with Avogadro's number, and we then arrive, if we insert the values which we have extracted for copper, at 8.491 times 10 to the power of 22 atoms per cubic centimeter of copper. That many copper atoms are within this small volume here. And now we get to the third step, which is about calculating the amount of charge in the wire volume. And to obtain the number of atoms in the wire, we can easily exploit the fact that the ratio of atoms per volume is constant. So we can use this ratio here to say that the number of copper atoms per cubic centimeter divided by the volume is the same as the number of copper atoms in our wire divided by the volume of the wire. And if we rearrange this formula to get to the number of copper atoms in our wire, we can easily say that it's the product between the number of copper atoms in the cubic centimeter times the volume of the wire divided by the volume of 1 cubic centimeter. We have previously discussed the concept of valence electrons, and we also have looked at the atomic model of copper, which you can see down here below. And copper has one single valence electron on its outermost shell, and this is why the number of atoms within the wire also corresponds to the number of free electrons, which are free to move about in between the spaces of the wire atoms. So the total charge Q within the wire, which is free to move, corresponds to the product of the number of atoms in the wire and the elementary charge. Let's first compute the volume of the wire, which is simply A times L, and then we can say that the number of atoms in the wire is identical to the number of free electrons in the wire, which is the product between the volume of the wire, A times L, multiplied with the number of atoms per cubic centimeter. And this equation here is a very important one, as it will lead us directly to a definition of the electric current, which we will arrive at in the next video to come. So let's run the numbers on a concrete example here to put our equations to the test. So we want to find out how much charge moves through the wire in a given time TL. TL is the time it takes a single electron to move over the entire length of the wire from start to finish, so to speak. And in the first step here, what we did there is to replace the time TL by the ratio between length of the wire and the drift velocity. And by expanding the expression for Q with the equation which we have just derived on the previous slide, we can get to the third step here, which consists of multiplying the elementary charge with the volume of the wire with the amount of electrons in a cubic centimeter of the material. So this expression here is nothing more than Q. Then we multiply it with drift velocity and we divide it by L. The L's cancel themselves out, so this equation here describes the amount of charge flowing through the wire in a given time TL. And as you might note, the unit L is no longer part of the equation. So even though we have it as one very important parameter which describes the shape of our cylinder here, which makes up the wire, it's no longer part of the equation here. Now let's insert some numbers, and we first insert the elementary charge, then the surface area of the wire, then we multiply it with the amount of the number of charges in a cubic centimeter of the wire material, and we multiply it further with the drift velocity of the electrons propagating through the wire. And here in the last step, we cancel out some of the units, actually most of the units, and the only unit remaining is the ampere, which describes electric current, as you have surely heard about. So actually the value at which we arrived here, minus 117.8 amps, this is an electric current. We have not yet defined electric current, but by running the numbers here, by cancelling out all the different units, we arrive at something which already has the unit of electric current. And now it's time in the next video to look in depth at the sound definition of what electric current is. And this video here is the precursor to understand what will be going on in the next video to come. For now, that's all. I hope you enjoyed the video. If you have any questions, please do not hesitate to drop me a question down below in the comments. I wish you a nice day. See you next time here on The Fearless Engineer.